Welcome back to another fun, exciting Q&A episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
I am your substitute host for this episode, Heidi Campo, and joining us is Professor Fred Watson, astronomer at large. How are you doing today, Fred?
Very well, thanks, Heidi, and great to see you as always. And I hope you're well, and I hope you're surviving the thunderstorm that apparently is going on around you at the moment.
It is. Like I just said, I would rather have a thunderstorm than a hurricane because I am here in Space Center, Houston. Not Space Center, Space City. I'm not in the Space Center. I'm in Space City. We did have a hurricane last year. That was not fun. I was alone. My husband was traveling at the time for work, and I had a broken foot in my neighbor's tree. The trunk didn't fall, but almost all of the big branches did. So I was out there with a broken foot, brace on my leg, crutches, and a chainsaw trying to chop up these branches and dealing with my first hurricane. And then we didn't have power for 9 days. It was awful in the middle of July.
Oh, that's awful.
So
How did
those
you survive
of you,
that? Oh,
I guess I just sheer will, I guess. But those of you who live in climates where you don't get hurricanes, enjoy those. Speaking of, looks like our first question today is from Jakob or Jacob, if I'm saying that right. I think it's Jakob from Norway. That is, they do not get any hurricanes there. You are safe from hurricanes and you get to enjoy the auroras. Jakob's question is, hi, this is Jakob from Norway. I'm working on a presentation about Planet 9 for my school where I will be comparing the mathematical prediction of the 9 planet with Urban Lee Veriner's, you'll have to correct me on that, Fred, work to finding Neptune in 1864. Lee Verner saw that something was wrong with the orbit of Uranus and figured out that it was getting pulled on by another planet. He told astronomers exactly where to look for this planet, and surely enough, they found Neptune on the first night of looking. What are the odds of that? Now, almost 200 years later, scientists see something wrong with some objects in the Kuiper belt and say that, say that another planet may be causing these strange orbital paths. My question is, why can't we predict exactly where Planet 9 is like Lee Verner did in 1864? Have we gotten worse at maths? Thank you for the great podcast.
And thank you for the great question, Jakob, because you've hit the nail on the head there. You're quite right about the discovery of Neptune. It was it's usually said that Neptune was the first planet discovered with the point of a pen, because it was calculations by Leverrier and also actually a British astronomer. I think his name was Adams, I might be misremembering that, who did the calculations at the same time and also predicted the existence of another planet, but he couldn't get anybody in England interested in actually following up on it. Leverrier basically was fortunate in having the director of the Berlin Observatory to help him out, and that was when Neptune was discovered, exactly where it was predicted. Now, Planet 9, you're absolutely right. There's a nice link there between 1846 and the early 2000s, because it was back in 2016 that 2 American astronomers figured out that there was something about the orbits of objects, as you mentioned, in the Kuiper belt, which are aligned in a way that suggested that there's another planet out there that's pulling them all into this alignment, this orbital alignment. But we haven't found it yet, and some suggest that it doesn't exist at all. And the difference between the discovery of Neptune and the search for Planet 9 is that Neptune, the prediction of Neptune's existence was based on very accurate observations of one object, which was the planet Uranus in the outer solar system. And it was what we call perturbations in the orbit of Uranus. But that that means it's being pulled out of what it would normally, what you'd normally expect to see. And it's that pulling that was attributed to Neptune. And you can then, because you're only looking at, well, 3 objects, the sun, Uranus, and the other whatever mystery body it is, which turned out to be Uranus, you can do the calculation and predict pretty exactly where you're going to find the as yet unknown object. And that's what happened. It's a great story with lots of twists and turns. It's a bit different with Planet 9. What we're seeing is the suggestion that some of the orbits of these Kuiper Belt objects are aligned in a way that means that they're being pulled out of a different orbit by a hidden planet. But you're now talking about not accurate positions of gravitational pulls. You're talking about statistical discussions, because you're talking about many objects and you're talking about many orbits. And one of the reasons why this is such a difficult problem is that if there was an object pulling these Kuiper Belt objects into their elongated orbits, into their aligned orbits, it would be a very long way away from the sun. It would be very faint and very difficult to see. But the other thing is you can't be sure that you're not seeing a statistical fluke. And a number of scientists have pointed this out, that maybe the Kuiper Belt objects, these icy asteroids beyond the orbit of Neptune, those objects are just a small sample of what is a bigger sample that we have not yet discovered. And if we could see the whole sample, there wouldn't be an issue. There would be no preferred alignment. So it's what we would call a selection effect. It's a statistical fluke. So that's the bottom line with this. It's a statistical business rather than a direct gravitational calculation, which is what it was for Neptune. So we haven't yet found Planet 9. A lot of people are still looking. I'm kind of hopeful that we will do, but the latest results suggest that maybe it's not there at all.
Sounds like machine learning may be a very beneficial asset in discovering these statistics and advanced formulas to find this.
That's right. I'm sure people are throwing AI at this problem. There's only so much you can do, though, because you're limited with the data set that you've got to start with, which is something like, I don't know, I think there are about 10 of these asteroids which are particularly aligned that suggest the existence of Planet 9.
This is true. Well, our next question is from Enrique, and this is an audio question that we will play for you now.
Hello, I'm Enrique from Portugal. Thank you for answering my last question about space-time. I have another one. How do black holes have density if the singularity doesn't have volume? Thank you. Bye.
It's always so sweet to hear from Enrique. You said he was what did we say? His last email said he was 6. So is that right, Fred? I think when they emailed us before, he said he was 6 years old.
Yes, that's correct.
Something like that. Yeah. No, Enrique. So cute. He's so smart too. I'm like, man, I was not thinking about this stuff when I was his age.
Yeah, me neither. Sorry, we're just to let our listeners know that we are improvising here. We're listening separately to, it might be Henrique rather than Enrique. Anyway, it's Henrique by the sound of it from Portugal. And I was listening slightly after you, so I could, so that's why you didn't get a response from me to your question, which I'm sure Hugh will tidy up when he edits this whole thing. His question was, how can an object have density when it's got zero volume? I think I'm paraphrasing that correctly. And Henrique has gone straight to the nub of the matter with a black hole, because a black hole is effectively defined as a point in space which has infinite density. Now, black holes have mass, and we can measure different masses for black holes. Some are supermassive black holes, which have masses millions or even billions of times the mass of the sun. Some are stellar mass black holes, which are similar in mass to the sun, but they all have mass. If they don't have volume, though, you'll remember, maybe you don't know this formula, Enrique. I don't think I did when I was 6. But density is mass divided by volume. If volume is 0, and that's the way we think a black hole is, then the density is infinite. Because if you divide something by 0, the answer you get is infinity. 2 very odd mathematical quirks. So it's possible that real black holes don't have infinite density, but their densities are very, very high, because a black hole, by definition, is either 0 volume or at least a very, very small volume. So it's a great question. And what you've done is you've basically gone to the heart of what defines a black hole. Well done.
And we absolutely need more young people interested in this stuff. I
Do we
saw,
not?
I'm actually, I'm going to brag for a second. I am a brand new aunt for the first time. I had my first nephew. So shout out to baby Roman. So excited you're here. But I was looking through baby books, and I guess they have the cutest little baby books these days. You can get quantum physics for babies,
Yes.
Astronomy for babies, math for babies. They have all sorts of cute little books. And I am so excited because I'm going to buy him all the science books in the world, because their brains are little sponges and they can learn so much so fast. And I'm like, you know what we should do is we should have little kids solving these problems, because they would probably come up with the answer faster than an adult would.
Let's take a break from the show now to tell you about our sponsor, Saily. Now, if you're planning your next adventure overseas, you can stay connected effortlessly with Saily. It's an eSIM app designed for modern travellers. With Saily, there's no need to swap a physical SIM card in your phone or hunt for local providers. Simply download the app, choose from an affordable array of data plans starting at $1.99, and activate your eSIM instantly. I've done it. I've used it in recent trips, and it works seamlessly. Now, whether you're exploring the streets of Tokyo or just relaxing on a beach in Bali, Saily has you covered. In fact, they are available in over 195 countries. But they offer more than just connectivity. Saily has built-in security features like virtual location changes, ad blockers, and web protection, all at no extra cost. And it's compatible with most eSIM-enabled devices, including iPhones, Samsung Galaxy, and Google Pixel. Saily ensures a seamless experience, and I know that's true. Plus, they have 24-hour, 7-day-a-week customer support with access just a tap away. If you're ready to simplify your travel connectivity, visit saily.com/spacenuts and use the code word spacenuts for an exclusive discount. That's saily.com/spacenuts. Saily is your passport to seamless global connectivity. Saily, S-A-I-L-Y, saily.com/spacenuts. Now back to the show.
0G, and I feel fine.
Space nuts.
Well, our next question.
Congratulations on your on being an aunt.
Thank you so much. Oh, I'm so excited. He's so cute. Our next question is from Ben. Ben, looks like you're emailing us from Northwestern University. Ben says, I don't know how common it is, but I do know for certain things like gravitational wave detections, many observations will drop, or many observatories will drop what they're doing to attempt to observe the source of the waves. I have 4 questions about this. 1, is it common for observatories to do this? 2, for what sort of events do observatories do this? 3, are there any sort of observations which are immune to these interruptions? And 4, my understanding is that observing time is quite constricted, highly scheduled, and difficult to obtain. So how do they compensate for these interruptions? Do they just move the entire schedule back? Do they just find a different slot for the observations that were interrupted while keeping most observations unimpacted, or something else?
Thanks, Heidi. And Ben, that's a question that I don't think we've ever been asked before on Space Nuts. And it's a really good question because it's part and parcel of the work of your average observatory. And so the first of your 4 questions, is it common for observatories to do this? And the answer is yes. These are effectively what we call target of opportunity observations, where the scheduled use of a telescope, and you're absolutely right, those schedules are laid down months in advance. People have applied for telescope time, sweat blood and tears to actually get their applications in and succeed in winning the telescope time. I used to do this quite a lot back in the day. Typically on the Anglo-Australian telescope, which is the one I used most, the biggest visible light telescope in Australia. Typically for every night of available observing time, there will be 3 to 4 different groups wanting to use it. So that's the level of competition that there is. And of course, only one wins out. And the result of that is you might be allocated 2 or 3 nights, or 4. I occasionally got 4-night allocations, where you're at the mercy of the weather and at the mercy of all the instruments working, but you've worked so hard to get that time. The last thing you want is for somebody to come along and say, oh, there's been X, Y, or Z happening in the space, we're going to grab your telescope. But it is sort of built into most observatories that is a potential way of operating. I guess some don't, but certainly at the Anglo-Australian telescope, these target of opportunity observations were made. So, Ben, your second question is, for what sort of events do observatories do this? Well, as you said, it's, some of the gravitational wave detections in recent months of neutron star collisions, where there might be a radio or optical counterpart, in other words, a flash, either in the radio spectrum or the visible light spectrum, then the target of opportunity rules would kick in, because there would have to be rules about this. It works, I think, for radio telescopes as well. I don't have any direct experience of observing on radio telescopes, but I do know about the other kind, the optical telescopes. And yes, your time will be taken over. So neutron star collisions. Supernovae is the most common one. If you've got a bright supernova and you have a telescope that's got the right equipment on it, you will probably turn to that to detect the supernova explosion and measure its spectrum at the peak of its intensity. That's happened a lot. Gamma ray bursts, the visible light counterparts of things that are detected by gamma ray satellites, that's happened too. So these things are, there are several what we call transient phenomena for which this kind of observation would be made. Number 3, are there any sorts of observations that are immune to these interruptions? Well, that would depend, I think, on the policies of the particular observatory in question. There might well be. Certainly at the AAT, there weren't. We did a lot of routine survey work where we were building up large catalogues of information on things, and that would be very much something that could be interrupted by a target of opportunity observation. And 4, my understanding is that observing time is quite constrained, highly scheduled, and difficult to obtain. Indeed, it is. So how do they compensate for those interruptions? Do they just move the entire schedule back? No, they don't. What they do is the astronomers who've lost the time really have to face the fact that they've lost the time. And that might be, one of the conditions under which they accept the telescope time in the first place. Often, though, there will be moves to try and compensate for that loss of time. And that's the last part of your question. Do they just find a different slot for the observations that were interrupted while keeping most observations unimpacted? That's basically the way it works. And in the case of the Anglo-Australian telescope, we had there was a small amount of time that was not allocated to users. We called it director's time because it was at the director's discretion to allocate that time, whether it was for hardware improvements or whatever, tests, things of that sort. But that is what normally would happen. The director would try and allocate some of his director's time to compensate for somebody who had lost time because of a target opportunity observation. And a great question. Thanks very much, Ben.
And I can attest to that. My good friend, Dr. Allison McGraw, she's a planetary scientist over at the Lunar and Planetary Institute, and she is always competing to get the best telescope time.
Yeah.
She was just in Hawaii not too long ago, and she was so excited because it was perfect conditions, and she got everything she wanted.
Very good.
3, 2, 1.
Space nuts.
All right. So this brings us to our very last question for the evening, which is from Fenton. And this is an audio question that I will play for you now. I'll give Fred just a second to get synced up with me.
Yeah, synced up
And then
now.
we can both hit play at the same time and listen to Fenton's question, which you will hear now.
Hey, Fred and Andrew, this is Fenton from St. Paul, Minnesota in the U.S. I understand you guys need some questions, so here's one for you to think about. I really like, by the way, everything that you do with the questions, whether they're good or bad. You always do a good job of coming up with something interesting on them. So, you guys talk a lot about gravity waves. And I asked myself, can you compare a gravity wave to a geometrical wave? That is a sinusoidal wave or a sine wave that's going to have regular minima and maxima to it. So what do you think of that? Does that make any sense? And then if that were the case, I thought, can two gravity waves interact? Can they either double their intensity or nullify each other? Can they be in phase or out of phase is another way of looking at it. And then, if we want to continue this classical analogy of speed is equal to wavelength divided by time, can one gravity have a wavelength that, for example, would be 1/2 that of the others? In other words, you'd have a sort of phase shifting there, maybe. I'd love to hear what you think about it. I hope you like the question. Keep up the good job. And stay warm down there. Bye now.
Well, that was a very nice question. Thank you so much, Fenton. I will stay warm. It's nothing but warm here in Houston in the summertime for us.
Yes, I can imagine. So, Fenton, that's a good set of questions. And the answer to most of your questions in there is yes. The gravitational waves are waves. They're basically vibrations of space. And you probably know that the waves that we're normally familiar with, like sound waves, are what are called longitudinal waves. The molecules of air move backwards and forwards as the wave progresses, whereas light waves are transverse waves, which are a vibration of the magnetic and electric fields, which are exist at any given time. So they are sinusoidal, is the way you describe them. Gravitational waves are something different. They're called quadrupole waves, and they're a bit like sine waves, but they've got a sort of rotational component to them as well. So they are not exactly like a light wave, but they are similar in broad characteristics. And in particular, they are similar in that, yes, they can interfere with one another. That's the phenomenon that you were talking about, where light waves can either cancel out or add to give you these, what we call fringe patterns. Gravitational waves can do that as well. The quadrupole waves can interfere with one another. And you're also right that they come in different wavelengths. We normally think of it as different frequencies. So gravitational waves caused by different phenomena have a very, very wide variation in frequency. Some are what we call let me just tell you the ones that we've observed so far, and that's because the particular gravitational wave detectors that we have are tuned effectively to these frequencies. They're the ones that come from colliding neutron stars, colliding black holes, all of that sort of thing we were just talking about a few minutes ago. And they are more or less in the audio frequency spectrum. So if you amplified them enough, you could hear them. They're, a few hundred hertz. Where 1 hertz is 1 cycle per second. But some of the bigger phenomena in the universe, and I'm thinking now of things like the Big Bang or the epoch of inflation, times in the universe when things were very different from what they are now, they generate what we call nanohertz waves, where the frequencies are measured in billionths of a hertz rather than a few hundred hertz. So they would be detected in a completely different way. And in fact, we think one of the ways of detecting them might be from the cosmic microwave background radiation, the flash of the Big Bang that we can still see. So you're right on the money with all of those questions. Yes, gravitational waves do behave almost in an analogous way to light. They certainly travel at the same speed of light. They can interfere, and they do come in widely different frequencies.
Well, excellent. Thank you. Thank you so much, Fred. These have been wonderful answers to some wonderful questions. And thank you so much to everybody who has written in. We really do have some of the best listeners here. I mean, this podcast, we have such an amazing, engaged audience. I mean, you guys are half of the show. Really, your questions are half of the show. So please stay curious. Keep sending in your wonderful questions. It's certainly so fun for me to hear Fred answer them, and it's a good time. Fred, do you have anything else you want to say before we sign off for today?
No, just keep the questions coming in, folks, because this is the thing that makes Space Nut special. We've got such a wide audience all over the world. We love hearing from you, and we love your questions, tricky ones or non-tricky ones alike. Thank you. And thanks to you, Heidi, too.
Oh, thank you, Fred. You're so sweet. All right. Well, this has been another Q&A episode of Space Nuts. We are Heidi and Fred signing off.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.